Good morning, everyone. We're going to go ahead and get started. Welcome to Windows 10 Segment Heap Internals. We are in South Seas C. Your speaker today is Mark Vincent Yassen. So before we begin, just a couple of brief notes. You'll be hearing these over the course of the day. Please stop by the business hall, which is located downstairs in Bayside AB. The Black Hat Arsenal is on the Palm Foyer up here. And of course, the Arsenal reception is at 5 p.m. If you haven't picked up your merchandise, today is your last chance to visit the Black Hat Swag and Bookstore. And we encourage you to visit the Kali Linux Lab in Mandalay Bay A. Thank you for putting your phone on vibrate. Without further ado, your speaker.
Okay. Good morning, everyone, and thanks for attending my talk. I'm Mark Vincent Yassen. I'm from IBM X-Force, and today I'm going to share with you my research of the new heap implementation in Windows 10 called the segment heap. My talk consists of 3 parts. The internals, where I'll talk about the architecture and different components of the segment heap. The security mechanisms, where I'll talk about the different mechanisms in place that make it difficult or unreliable to attack heap metadata, and in certain cases makes it unreliable to manipulate the layout of the heap. Case study is where I'll discuss and how to manipulate the layout of the heap that is managed by the segment heap in order to reliably leverage memory corruption vulnerability for an arbitrary write in the context of the edge content process. And the demonstration will follow. Some notes before we proceed. A very detailed white paper is available, which you should be able to download from Black Hat's website sometime after this talk. And it contains the details about the data structures, the diagrams of the algorithms, and names of internal functions in case you are interested in doing your own research of the segment heap. Also, this paper and presentation is based on the 64-bit and TDLL from Windows 10 Redstone 1 preview build 14295. So with that, let's begin. Here's the architecture of the segment heap. It consists of 4 components. The backend part here uses the NT Memory Manager APIs for creating and managing the segments where backend blocks are allocated from. And on the top of that is the low fragmentation heap, or LFH. It is similar in purpose to the LFH in the older heap implementation, but as you'll see later, the data structures used are different. The LFH depends on the backend for creating the LFH subsegments where the LFH blocks are allocated from. Another component on the top of the backend is the variable size allocation component, or VS. It also uses the backend to create the VS subsegments where VS blocks are allocated from. From its name, its difference from the LFH is that in VS, the blocks in the VS subsegments are variable in size. It starts with a large free block, and then it is split into different sizes as allocation request comes in. Finally, the large blocks allocation component here services a large allocation request. It directly uses the NT Memory Manager APIs for the allocation and the freeing of the large blocks. Another part to notice is that for allocation sizes less than or equal to 16,368 bytes, the allocation request will only be serviced by the LFH if the LFH bucket for that particular allocation size is activated. If not activated, it will be serviced by the variable size allocation component. So when is the segment heap enabled in a process? So currently it is an opt-in feature. Windows app, formerly called Modern or Metro apps, are opted in by default. This includes apps from the Windows Store and, more importantly, Microsoft Edge. Dependencies or components used by Edge that do not use a custom heap manager will use the segment heap. Additionally, executables with those listed names are also opted in by default. This encompasses the different system processes. The older heap implementation, the anti-heap, is still the default use for traditional Win32 applications. If you want to enable or disable segment heap for a particular executable, you can use the front-end heap debug option in the image file execution options registry entry. Or if you want to enable or disable segment heap for all executables, you can modify the enabled entry in the segment heap key under the current control session manager registry key. So for an illustration, here's the edge content process heaps when edge is initially loaded. As you can see, the default process heap, the first heap in the list, is managed by the segment heap. Also, the MSVCRT heap, the third heap in the list, is also managed by the segment heap. A thing to note that even if a segment heap is enabled in the process, not all heaps created by the process will use the segment heap. Example of these are the shared heaps and heaps that are not growable. In the illustration, the second heap is a shared heap, and therefore it is still managed by the anti-heap. Next, in this presentation, I will be mentioning about the heap base. The heap base is the address returned by heap create or RTL create heap when the heap is created. You can quickly check if a heap is managed by the segment heap by looking at the D word at offset 10 hex. If the value is DDEE, it means that it is managed by the segment heap. At the top of the heap base is the segment heap structure here. It contains the state of the 4 segment heap components, such as the large block allocation, the backend. The structures for tracking the VS and LFH state are more complex, and therefore they are stored as a substructure called VS context and LFH context. Also, since the LFH buckets are dynamically activated at runtime, instead of being stored in this LFH context, the reserved memory below the segment heap here is dynamically committed to store LFH bucket-related structures. And that is why the lower part of the heap base is called the LFH context extension. So after discussing the architecture and configuration and the heap base, I'll now discuss the 4 different components of the segment heap. And I'm going to start with the backend. So the backend is used for allocation sizes greater than 128 to 508 KB. And the backend blocks have a page size allocation granularity. The backend operates on segment structures here, which are 1 megabyte chunks of virtual memory allocated via NT-allocate virtual memory. And the segments owned by the heap are tracked by the segment list head found in the heap base. And the segment consists of 2 parts. The segment header and the data part where the backend blocks are allocated from. So zooming in on the segment, so the header consists of page range descriptors here that describes each page in the segments. There's 1 page range descriptor for every page. For example, page range descriptor 2 describes this page, and page range descriptor 3 describes this page. One of the main fields in the page range descriptor is the range flag here. It is a bit flag that describes whether the page is committed or busy or allocated. Next, because backend blocks can span multiple pages, there is what is called first page range descriptors, which are basically the page range descriptor for the first page of the backend block. First page range descriptor are marked as such by the first flag in the range flag field. And they have additional field set, such as the size field, which is equal to the size of the backend block in pages. Finally, another important item to discuss is that for free backend blocks, their first page range descriptor is inserted to a backend free tree. And when inserting the first page range descriptor, the key field here is used. I'll further discuss the backend free tree and the key field in the later slide. Here is an example of a set of page range descriptors that describes a busy block. Page range descriptor 2 describes this page, and then page range descriptor 3 describes this page. They state that the pages are both committed here and then allocated, which means busy. Also, the page range descriptor for page 2, which is the start of the block, is marked as the first here. And therefore, the size field is the total number of pages of the backend block. So to track the free backend blocks, the first page range descriptor of free backend blocks, as I previously mentioned, are inserted to this backend free tree. The key used for inserting nodes to this backend free tree is a word size value, in which the high byte is the number of pages of the backend block. So here, 23, and then 21, and then 4F. And the low byte is the encoded commit count. Now, encoded commit count is equivalent to the bitwise NAT of the number of committed pages that the block has. In this example, the blocks are fully decommitted, and that's why their value are FFX. The key is set up this way so that when searching for free backend blocks, a best fit search is done, and the most committed blocks are given preference. So in other words, if 2 blocks with equal size will fit the allocation request, the most committed block will be selected. So for allocation, as I mentioned, best fit search is done with the most committed block given preference. If a large block is selected, the large block is split. And for freeing, the to be freed block is coalesced with neighboring free blocks to reduce fragmentation. So that's the backend, and now the second component, the variable size allocation. Variable size allocation, or VS, is used for allocation sizes less than or equal to 128 KB and has 16 bytes allocation granularity. BC blocks have a 16-byte header at the beginning of each block, and VS blocks are allocated from VS subsegments here, which are just a special type of backend block. And VS subsegments are tracked using the subsegment list here, found in the VS context field in the heap base. And then zooming into a VS subsegment, 2 of the most important fields is the commit bitmap, which tracks which part of the VS subsegment are committed, and the other one is the size of the VS subsegment. So after offset 30 hex is where the VS blocks are located. So when a new VS subsegment is created, the whole area here is one larger free block. It is just split into different sizes as allocation request comes in. So of all the different components of the segment heap, only the VS blocks have a header at the beginning of each block. BC blocks have a 16-byte header here. And the first 8 bytes are encoded. I'll discuss the encoding in the security mechanisms part of the talk. So the first 8 bytes of this BC block header is also found in the header of a free BS block. And the memory cost field is only significant in free BS blocks. It is a value computed based on how much portion of the free BS block is committed. The more portion of the free block the more portion of the free block is committed, the lower the memory cost is. So unsafe size is the size of the block, and the unsafe previous size is the size of the previous block. And the allocated field is a non-zero value if the block is busy. So another important field is the bit here. It is a news bytes field. It is the bit that means that there is a difference between the user requested size and the total block size, which happens due to the allocation granularity. The value of the difference is stored at the end of the VS blocks in the last 2 bytes. Finally, the free VS blocks are node of the VS free tree, and that is why there's a node field here starting at offset 8. So similar to the backend, VS also has a free tree for tracking the free VS blocks. The nodes of the free tree are the free VS blocks header, and the key for inserting nodes to the free tree is a ID word size value, in which the high word is the size of the block here, 0101, 00F8, and then 00301. And the low word is the memory cost, which I previously discussed. The more committed portion of the block, the lower the memory cost is. So similar to the backend, the key is set up that way so that when searching for free BS blocks, a best fit search is done with the most committed blocks given preference. In other words, if two BS blocks with equal size will fit the allocation request, the most committed block will be selected. For the allocation, as I mentioned, best fit search with a preference to the most committed block is conducted. And large free blocks are split unless the size of the resulting remaining block will be less than 20 hex bytes, because the 20 hex bytes is the size of a free BS block header. So for freeing, the to be freed block is coalesce with the neighboring freed blocks to reduce fragmentation. So that's the backend and the VS allocation component. Now we go to the low fragmentation heap. The low fragmentation heap, or LFH, services allocation requests for less than or equal to 16,368 bytes, and the allocation granularity depends on the allocation size. So similar to the LFH in the NT-heap, the LFH prevents fragmentation by allocating similarly sized blocks from larger pre-allocated blocks of memory, which in this particular case, the LFH subsegments. LFH subsegments are just a special type of backend block, and LFH bucket-related structures here, which are allocated from the LFH context extension, points to these LFH subsegments. Allocation sizes are distributed into buckets. So initially, all buckets are not activated, and for each bucket, there's a counter tracking the allocation and free requests for the allocation sizes corresponding to the bucket. The bucket is activated on the 17th active allocation for the bucket's corresponding allocation size. And another way to activate the bucket is if the allocation request for the bucket's corresponding allocation size reaches 2040, regardless if the blocks were previously freed. So another concept of LFH is the affinity slots. Affinity slots actually own the LFH subsegments where the LFH blocks are allocated from. And the heap manager assigns processors to these affinity slots. So initially, when the bucket is activated, only one affinity slot is created, and all processors are assigned to it. So now imagine that this processor here is assigned to this affinity slot. So contention in accessing these LFH subsegments can occur. So if there's too much contention detected, when the LFH subsegments are accessed, a new affinity slot is created with their own set of LFH subsegments, and the processor is reassigned to this new affinity slot. So LFH subsegments are where the LFH blocks are allocated from. The top of the LFH subsegment is the heap LFH subsegment structure. Some of its important fields are the free count field, which is the number of free LFH blocks in the subsegment. And another is the block count field, which is the total number of LFH block in the subsegment has. So another important fields are the block size field and the first block offset field, which are both encoded. The encoding I will talk about later. So finally, the block bitmap is which tracks the state of LFH blocks if they are busy or they have unused bytes. And the LFH subsegment metadata, and so after the LFH subsegment metadata here are the LFH blocks here. So focusing on the LFH block bitmap, each LFH block in the subsegment is represented by 2 bits in the block bitmap. The first bit is the busy bit, and the other bit is the unused bytes bit. If the unused bytes bit is set, it means that there's a difference between the requested allocation size and the total block size, which happens due to the alignment to whatever the allocation granularity is. The difference is stored in these last 2 bytes of the LFH block. Also, the LFH block bitmap is divided into 64-bit chunks, which I call the bitmap bits, and each of these represents 32 LFH blocks. The allocation from the LFH is different because it involves some randomization. For the allocation routine first select bitmap bits from the block bitmap, in which the starting point is depends on a free hint. So once a bitmap bit is selected, it will randomly select a bit position in the bitmap bits where the busy bit is clear. So once a random bit position is selected, it will set the busy bit and, if necessary, the unused byte bit. The illustration shows an actual result of the allocation randomization, whereas the first allocated block is here, and the second allocated block is here, and the third allocated block is here, and so on. For freeing, among other things, the blocks busy and unused byte bit from the block bitmap is cleared. This is just a simplified explanation of the LFH allocation and freeing. And for a more detailed explanation, please refer to the white paper. And finally, the fourth component of the segment heap, the large block allocation component. The large blocks allocation component handles allocation requests for sizes greater than 508 KB. Large blocks are allocated and freed using the virtual memory functions provided by the NT Memory Manager. The large block here do not have a header at the beginning of each block. Instead, the metadata for each block are allocated from a separate metadata heap. And for the heap manager to identify if the block is a large block allocation, its address is marked as large depending on the large allocation bitmap here. So the large allocation is straightforward since there's no free list to consult. First, the block's metadata is allocated from a separate metadata heap. Then the block's virtual memory is allocated. And then the block's address is marked in the large allocation bitmap. The freeing is also straightforward. This is just the reverse process of the large block allocation process. Before ending the internals part of the talk, I want to discuss the block padding, which will affect the layout of the segment heap blocks. Just in case you are investigating a fraud process in which the segment heap is enabled, but that process is not opted in by default to use the segment heap, take note that there will be a 16-byte padding added before the user data portion of the block. As shown, this is a modified layout of the backend block here, and a busy block here, and an LFH block. So to summarize, there are 4 components of the segment heap: the backend, the VS allocation, the LFH, and the large block allocation component. The data structures of the segment heap are largely different compared to the data structures of the NT heap, and free trees are used instead of a free list. Of all the components, only VS blocks have a header at the beginning of each block, and the best fit search algorithm with a preference to most committed block is used by the backend and the VS component, while the LFH allocation, the selection for the free blocks are randomized. So that's it for the internals, and in the second part of the talk, I'll discuss the mechanisms that are added in the segment heap that make it difficult or unreliable to attack heap metadata, and in certain cases make it unreliable to perform heap layout manipulation. The security mechanisms is well known. The subsegment and segment lists are linked lists. So to prevent classic arbitrary writes due to corrupted linked list nodes, checks are added when removing and inserting nodes from a linked list. If the check failed, the fast fail mechanism will be triggered, and this will cause the process to terminate immediately. So similar to linked list node corruption, an attacker is also, if an attacker can also cause an arbitrary write if 3 nodes are attacker controlled. In this example, the attacker may have controlled the parent value of this left child. If that is the case, when the parent of this left child is manipulated, an arbitrary write may occur. So to prevent this, the NTDL functions for manipulating the arbitraries will follow the parent value and then check if one of each child is indeed the left child. And if not, there will be a failure in validation. It will cause the fast fail mechanism to be triggered, causing the immediate process termination. Next, to make it unreliable to guess the heap address, a random size free memory is created before the heap base. And this random size is a multiple of 64 KB. Then to prevent overflow from BS blocks here, and from LFH blocks here, from correcting data outside the subsegments where they are located, guard pages are added at the end of VS subsegments here and the LFH subsegment. So also to prevent an overflow from corrupting data outside the large block, a guard page is also added at the end of the large block here. And backend blocks, on the other hand, do not have a guard page, allowing an overflow to corrupt adjacent data outside the backend block. Next, there are function pointers stored in the heap base. Assuming that an attacker is able to determine the address of the heap and that an attacker has a control flow guard bypass, one way to control execution flow is to modify the function pointers found at the heap base. To protect these function pointers from trivial modification, they are encoded using the heap key and the VS context address or the LFH context address. Next, VS blocks have a block header at the beginning of each block, and these headers here are potential target for overflows. To protect important parts of the VS block header from trivial modification, they are encoded using the LFH key and the block address. So similarly, the LFH subsegment headers also have some important fields that an attacker may leverage. Again, to protect these important fields from trivial modification, they're encoded using the LFH key and the LFH subsegment address here. Then finally, to make exploitation of LFH-based buffer overflows and use after freeze unreliable, as I previously discussed, the LFH randomly select which free LFH block to use. This makes it unreliable to place a target LFH block adjacent to a LFH block that can be overflowed. It also makes it unreliable to reuse a recently freed LFH block in case of user use after free exploits. To summarize, important metadata encoded, linked list nodes and tree nodes are checked. Detected corruption will cause an immediate termination of the process. Guard pages and some randomization are added. Also, it will be difficult to perform a precise layout manipulation for the LFH due to the randomization. But the backend and VS allocation, which do not use randomization, are more welcoming to heap layout manipulation. In the final part of the presentation, I'm going to talk about how the layout of BS allocations can be precisely manipulated. In this final part of the presentation, I'll discuss the layout of how the layout of heap managed by the segment heap can be manipulated. I'll use a vulnerability in the Windows PDF library that I discovered and was patched by Microsoft last March. First, the vulnerability in this case study is found in the WinRT PDF, a built-in PDF library in Windows since Windows 8.1. One interesting aspect of WinRT PDF is that it is used by Edge to render PDFs. Therefore, remote code execution vulnerabilities in this PDF library can potentially be used in edge drive-by attacks. So in the illustration, 25 by 25 pixel size embed element references a PDF file, which WinRT-PDF would then render. If the PDF exploits a remote code execution vulnerability, then an attacker may take control of the edge content process. The vulnerability that I'll discuss involves the PostScript operand stack. This PostScript operand stack is used when interpreting PostScript calculator functions embedded in PDFs. The PostScript operand stack is a vector of 65 hex C-type 4 operand pointers here. And each of these points to a C-type 4 operand structure, where the first D word is the type, and the second D word is the value representing the value in the PostScript operand stack. And this is where the segment heap comes to the picture. This PostScript operand stack is allocated from the MSVCRT heap. And in the context of the edge content process, this MSVCRT heap is managed by the segment heap. Now for the vulnerability, the issue is that the PostScript interpreter fails to properly validate if the PostScript operand index is already past the end of a PostScript operand stack, wherein it allows the PostScript calculator function to push a value to invalid index 65 of the PostScript operand stack. Now, if an attacker is able to implant an attacker control address right after the PostScript operand stack here, the attacker can perform a memory write operation to the attacker control address, thereby an arbitrary write. Now that we have an understanding of the vulnerability, the plan to implant the target address after the PostScript operand stack is as follows. So we allocate a control buffer and set offset 328 with the target address. And we free the control buffer. And when the PostScript operand stack is allocated, the free VS block of the free control buffer will be returned by the heap manager and will be used for the PostScript operand stack. So this looks like a good plan, but this requires the ability to allocate and free control buffers. Unfortunately, WinRT-PDF still does not support JavaScript embedded in PDF. That would potentially allow the arbitrary allocation of freeing of blocks from the MSBCRT heap. So that is a problem, and one solution is this. This is where the chakra and the chakras array buffer implementation comes in. Using JavaScript code in an HTML, an arbitrary size block can be allocated from the MSVCRT heap by instantiating an array buffer object. In the illustration, an array buffer with a 340 hex as the size instantiated. Because the data buffer of the array buffer is allocated using MSVCRT malloc, the data buffer is eventually allocated from the MSVCRT heap. And putting the arbitrary values inside the data buffer is as simple as executing the code here. If bucket activation is needed, we just need to sequentially instantiate 17 array buffers with the same size here. For freeing the data buffer, we just need to remove references to the array buffer and then trigger garbage collection. But again, unfortunately, collect garbage does not work in Edge. You can call it, but its functionality is disabled. But further looking at the array buffer implementation, the size passed to the array buffer constructor here is added to an internal chakra engine counter. If that counter reaches 192 MB in machines with more than 1 gig of memory, a concurrent garbage collection will be triggered. So to perform garbage collection, one just need to instantiate an array buffer with a size of 192 MB, and a delay is then introduced to let the garbage collection to finish, and then the succeeding JavaScript code is executed. So now that we have the capability to allocate a block and to free a block from the MSVCRT heap. But there's another problem to overcome. If the LFH bucket The problem is that the highest 16-bit of the target address will be overridden here by the unused bytes value. Even if a larger control buffer is allocated and freed, the heap manager will split the size to where there are still 8 unused bytes. So this is a showstopper because the target address will become invalid due to the corruption. Now, to solve this problem, internals of VS allocation can be leveraged. If we allocate and free a control buffer that is large enough so that there will be more unused bytes here, and small enough so that the free block of the control buffer will not be split, then the target address will remain intact here. So in this case, 340 hex bytes control buffer is allocated and freed. And again, there's another problem. This free block here may be coalesced with neighboring free blocks before the postscript open stack is allocated in its place, thereby reducing the reliability of the arbitrary write. Now, to solve that problem, instead of one control buffer, 15 control buffers are allocated. And in an alternating manner, 8 are left busy while 7 are freed to prevent the free blocks from being coalesced. So in an actual allocation pattern, some of the control buffers may be allocated in a different VS subsegment or allocate from separate larger free blocks. Therefore, the actual allocation pattern will not always exactly match the illustration, but nonetheless, this increases the chance that at least one or more free control buffer will not be coalesced. And then finally, there's another problem to be solved. Before the postscript operand stack will be allocated in one of these free control buffers, these free blocks may be used for a small allocation request, and they may be split, and therefore further reducing the reliability of the arbitrary write. Now, to solve that final problem, we just need to activate the LFH bucket for these smaller allocation sizes. So instead of the VS allocation component servicing them, the LFH component will handle the allocation request, therefore protecting the free blocks from unintended use. So to summarize, the JavaScript code in the HTML file will manipulate the layout of the MSVCRT heap using array buffers. Once the heap layout is manipulated, an embed element here referencing the proof of concept PDF file is injected to the page. WinRT-PDF will then load the PDF file and will then request for the allocation of the postscript open stack. The heap manager will return one of the free controlled buffer blocks. And there you go, the target address is implanted right after the postscript operand stack. And the PDF just needs to trigger the vulnerability, and the arbitrary write can be achieved. So if everything works as planned, in the demonstration you will see something like this, where WinDBG will be loaded as a post-mortem debugger to a crash edge content process. The crash is due to a write access violation here, where the address of the memory write operation is fully controlled here, and the high 32 bits of the value to write to is controlled. So I'll now start up the demo. This is the VM that serves the HTML file that manipulates the heap layout, and the proof of concept PDF that triggers the vulnerability. And this is the VM where Edge will be loaded. And here you go. As you can see, the target address is fully controlled, and the high 32 bits of the value is controlled And to verify, we are in the edge content process. So to summarize, the case study showed that precise layout manipulation is achieved in heaps managed by the segment heap. Specifically, it showed how the layout of VS allocations can be controlled and how the LFH can be used to preserve the controlled VS allocation layout. The two main elements that allow the precise heap layout manipulation in the case study was the scripting capability provided by the Chakra JavaScript engine and the common heap used by the Chakra's array buffer and WinRT-PDF port script interpreter. Finally, when developing proof of concepts, one might encounter issues that seem to be unresolvable, such as the target address corruption described in the case study. In cases such as those, understanding the internals of the heap implementation will sometimes provide the solution. To conclude, the internals of the segment heap and the NT heap are largely different, although some components of the segment heap and the NT heap have the same purpose. The data structures supporting them are mostly unlike their counterpart in the NT heap. Security mechanisms are comparable with the NT heap. Since the data structures are new, these new data structures are interesting for metadata attack research. So in terms of heap layout manipulation, the case study showed that given the capability to perform arbitrary allocation and free, precise layout manipulation of heap managed by the segment heap is achievable. Finally, I encourage you to read the white paper if you are further interested in this topic. These are some prior works and references. Additional references can be found in the white paper. And thank you for your time, and if you have any questions, just let me know. Thank you.